And like we said now, we have R3 and R4 in parallel, and so even though they're not really at the far end of the circuit from the source, we can combine them in parallel right now. And R6 and R7 are in parallel because they have the same voltage drop across them. And you know, I haven't really labeled the nodes, but the idea is that I could, let's say, all of this across here, right, is at the same voltage. So we can put an A up there. And then all of this over here is at the same voltage. And we can put a B up there. And then, you know, this node down here, we can call that C. Now, the problem with doing that, right, is that now, when I combine these two resistors, we said that one of our you know, things that we can do is to label that new resistance with an A. And if I got this node labeled A and this resistance labeled A, then we've got a bit of a problem there. So what I'm going to do then is I'm going to erase these labels on the nodes. And the idea is that, you know, everything connected here is at the same potential. Everything connected here is at the same potential. And everything connected to this large node on the bottom is at the same potential. Okay, so let's go back to our calculations. We have then, let's say, our A, and I actually started with 6 and 7. So our A equals our 6 in parallel with R7. It don't really matter where we start to. And so when it's just 2, we can do product over sum. So product over sum, 6 times 3 over 6 plus 3, or 9. And so this gives us 18 over 9, 2 ohms. And so if we're going to tackle R3 and 4 now as well, RB is equal to R3 in parallel with R4. And so again, it's just 2. We can use product over sum. 2 times 3 over 2 plus 3, which is 5. And this one didn't give us a whole number. So we got 6 over 5 and 1.2 ohms. So at this point now, it might be a good idea to redraw a circuit. And so I've taken the liberty of redrawing it, and I should now be able to select that, I think, and I'll copy that back to the main page over here, and we'll resize it. Now I'll put it here. I don't know how much room that's going to leave us to do our calculations coming back up this side of the page over here, but we hope for the best. Okay, so now we have then replaced R3 and R4 with RB at 1.2 ohms. We've replaced R6 and 7 with RA at 2 ohms, and so we're left with this circuit. We haven't touched R1 or R2, and if we think about what we've been asked for, V6 is the voltage here. So we still have V6 as the voltage across resistor A, right? So this is V6. And now the power of resistor number 4 we've been asked to find, and that's this resistor. So we got to go back more or less to the original circuit for that. But remember that V4 exists in this circuit. So, we can do V squared over R for power probably, and we don't need the current through R4. And so we maybe not need to go back to the original circuit at all. RT we're concentrating on, then RT is easy. Then the power supplied to resistor 4 and the voltage across number 6 is what we've been asked to find. Okay, so back to our resistors down here. Now, here, remember, RB and RA are not in parallel because R5 is in here. R1, R2, no series of parallel connections over here because of the presence of current division at this node here. And remember then that this node is the first one we drew up here. So now, so what we do have is the same current goes through 5 must go through A. So they're in series. So we said that RC is equal to R5, and to show series connection, we usually put in a little S. All S's and 5's might look the same. Okay, so then RA. And you can put a plus sign in there, of course, if you want. That might make life a bit easier. So R5 was 4 ohms. And RA was 2 ohms. So 2 of those in series for RC, 6 ohms. Now, if you can look at this circuit and say this branch here is connected between this node and this node, so it's in parallel with RB, then you can combine RB and RC in parallel and continue on. However, at this stage in the game, you might want to redraw it again now. And so I've redrawn to include RC to replace R5 and RA, and it's here. And so let me select that, copy, back to the main page, and I'll paste it here. And again, I'll resize it. Okay, so now we have RB and RC in parallel. Top end of each one connected together, the bottom end of each one connected together. That means a parallel connection. So I'll call this one RD, I guess. Is equal to RB in parallel with RC. And you might also note that VB here is still V4. V6 is not on this circuit, right? Okay, so RD then is the product over sum 1.2 ohms times 6 ohms over the sum, which is 7.2 ohms. And if you do the math there, you'll find that RD now does indeed work out to be a nice old number because it's 1 ohm. And so if you think about the original circuit up here now, R3, 4, 5, 6, and 7 are combined to give us just the 1 ohm. And so, maybe we might consider that an insignificant resistance compared to R1 and R2. Okay, so the idea now is that B and C gave us a small resistance, it's 1 ohm. And we can redraw the circuit once again if we wish. At this point, you might realize that R1 now is in series with RD, is in series with R2, and we can find RT relatively easily. Otherwise, what we want to do then is redraw again. And so we pick up this circuit and paste it here. and I have replaced our B and C with our D at 1 ohm. So now these three resistors, the total current in this circuit comes out of the source, positive terminal, flows through R1, flows through RD, flows to R2, and then back to the source. And so these three resistors are in series. And so our calculation for RT will give us RT is equal to R1 plus RD plus R2. And of course, we could have put our laces there to show that there's a series combination, but it's not necessary. We have now 10 ohms plus, this was supposed to be our D here, 1 ohm plus R2 at 8 ohms, and RT is equal to 19 ohms. And so now that becomes that is the answer to part A. Okay, so now Ohm's law says that IT is equal to VT divided by RT. And so remember that we didn't have VT is not the voltage drop across any resistor in particular, because its voltage division tells us it to be divided proportionally among R1, RD, and R2. And so we find the current by saying VT is 12 volts, and we divide that by RT, which is 19 ohms. And so now RT comes out to, and so this should be rounded properly now, and you should keep at least 3 significant digits. And so I wrote down 631.6 milliamps. So 4 significant digits there in that, and that should be a 6 there. And so, as a decimal, I suppose 0.63, and if you round it, you can 6.32 amps. And so IT. And that's the answer to part B. Now, IT flows through R1, and we can calculate a voltage drop V1. However, that's not really helping us solve the question that we're asked, and we can calculate V2. It's VD that's going to help us calculate or find the answers that we're asked for. And remember that the answers that we're asked for is the power, right, delivered to resistor 4, which is this one, and the voltage across resistor 6, which is this one. And, voltage V6 is equal to VA, because 6 and 7 combine to give us A. And so we'll work our way up to that. Now, so from this circuit here, we're going to say that ID, of course, is equal to IT, because, this is a simple series circuit, and we know that IT must go through all 3 resistors. So VD then is equal to ID times RD, and we have 0.63. I'll use 1/6. You can round it to 2 if you like. I'm having some trouble doing that neatly. Multiplied by RD, which was 1 ohm. And so now VD then is equal to 0. I did round this, 632 volts. And so, like we said, you know, a small proportion really of the source voltage, which was 12 over there. But that's okay nonetheless. So remember that if this is VD, you know, I already labeled it VB, we can bring this back to this circuit, and the two resistors that combined to make D was B and C. So therefore, up here now, we can say that VB is equal to VC is equal to VD from the simplified circuit below, and we know a value. And so our 4 up there was part of RD. Our 6 was also part of RD. And so we move up here, we'll note that our 4 was part of RB, and our 6 was part of RC. And so in actual fact, right, VB here, V4 was equal to VB. So at this point here, we can say that V4 is equal to VB, right, equals VD at 0.632 volts. I'm having trouble with clarity today. Okay, so our D in this circuit got 0.632 volts across it. We bring it up. The two resistors that made our D means that VB equals VC equals VD. And if we bring RB or VB up to this circuit and up to this circuit, 3 and 4 made B. So V4 equals V3 equals, we can put V3 in there as well, right? Is equal to V4 equals VB at 0.632 volts. Now remember that P can be calculated as V squared. Oh, I'm sorry, V squared. Just let me fix that for a second. V squared divided by R. And if we're applying that to resistor 4, then P4 that we're trying to calculate is V4 squared divided by R4. And so for that one, we should be able to do 0.632 volts, and we're going to square that, and we're going to divide it by the value of resistance for R4, which is 3 ohms. And if we do that, we're going to come up with, I'm going to squeeze that in here, P4 is equal to, and so this is less than a volt. We square it, of course, is less than 1. It becomes a small number, and I calculated 0.133 watts for that, and so I wrote down 133 milliwatts, and then that is the answer to part C. Okay, so the last one now that we're asked to find is V6, and V6 is this one. V6 is actually VA here, and so we don't know VA. What we know is VC, right? And so R5 and RA made up RC right here. So basically, we got VC, so we can find IC. And so let's do that right here. I don't know that I'm squeezing this in, but IC is equal to VC divided by RC. And so again now, that should be a C there. We have the 0.632 volts divided by RC, which was 6 ohms. And so the current IC is equal to I can't read my own writing. So 0.632 divided by 6 gives us 105.3 milliamps. I couldn't tell if it was a 0 or a 6 what I wrote down here, and milliamps. Now, so we have IC, and that is the current here, IC, if you're following. And so that means that when we go up to this circuit, this current here is IC. And so if I put the calculation up here, that means that I can calculate VA. And VA then is this voltage right here. So VA is equal to V6. And that is equal to IC multiplied by RA. And why is that? Because IC goes to that branch. So IC is equal to I5 is equal to IA. Now the reason for that, of course, is that R5 and RA made up RC. And so if I've calculated IC, I know the value of IA, and so I can write IA here, right? IA times RA. And we have then, just let me move that equal sign back a little bit. And we have here equals 0.1053 amps for IA or IC at 105.3 milliamps, all right? And we're going to multiply that by our A, which was 2 ohms. And so VA equals V6 now becomes 0.2105 volts. And that is the answer to the last part, which is part D. Oh, and so again, remember that R6 and R7 made up RA in a parallel relationship. So the rules of parallel circuit says that the voltage drop across this resistor is equal to V6 is equal to V7. So if we found VA, we have found V6.